For Lab 5, I will be analyzing the motion of a jumper on the human rope swing. The objective is to observe and analyze the motion of the rope swing. By analyzing the motion of the pendulum, find the net force on the jumper and calculate the parallel and perpendicular components of the force. Create a VPython model that calculates these forces. I will be pretending like the jumper is a pendulum using an ideal rope. For Newton's second law, which is F net equals mass times acceleration, I will be using the change in velocity to find the change in momentum, and I will find F net, which equals F net parallel plus F net perpendicular. The initial conditions: the initial velocity of the jumper is 0. The initial position was gathered from my tracker data. The length of the rope, I'm going to use real-world conditions, which is 130 feet long. The mass of the jumper is about an average 150-pound person, so 68.0389 kilograms, and delta T is 0.042, which was also gathered from my tracker data. A ball attached to a string to a fixed point and swung it as if it were a pendulum. I will use the points collected from this video analysis to use to calculate the F net perpendicular, and F net parallel components in my code. So I will be using each of these points as it swings along the pendulum. The first part of my VPython code collects the data from a CSV file, which contains the X and Y coordinates for each position of the pendulum. It takes these points and calculates the velocity from the data. It computes the X component of the velocity and the Y component of the velocity, and updates the time by saying T equals T plus delta T. This is the calculation loop, which will find F net. So first we use the velocity components to define the initial and final velocities. Second, we compute the initial and final momentum vectors. And after computing the momentum vectors, you can calculate the jumper's change in velocity and change in momentum. This will be updated over and over again throughout the code. After that, we can call it dp dt, which is delta p over delta t, which is equal to F net. Now we can calculate dp dt parallel by taking the magnitude of the final momentum subtracted from the magnitude of the initial divided by delta t, and you get the parallel component, which is the magnitude of dp dt times the p hat. You can use Newton's second law to calculate F net parallel by setting it equal to dp dt parallel, and we can calculate dp dt perpendicular by subtracting dp parallel from dp dt, and then use Newton's second law to calculate F net perpendicular by setting it equal to dp dt perpendicular. When we run the code, there will be 3 arrows showing each component. The yellow arrow represents F net, so the total net force. The blue arrow represents F net perpendicular, and the black arrow represents F net parallel. When we run it, it tracks the motion of the pendulum, and as you can see, the forces grow larger as it approaches the center equilibrium point of the pendulum, and they get smaller as they approach the end. They also change direction as the pendulum changes direction.